falar algumas palavras em inglês, depois eu passo para português. It's with great pleasure that I reintroduce you to Professor James Glimm, whose distinguished career I'll talk about in a second, and I was lucky enough to have him as advisor. Bom, é um enorme prazer para mim reapresentar o professor James Glimm, atualmente da Universidade de Stony Brook e também do Brookhaven National Laboratory. Eu tive a sorte de tê-lo como orientador de doutorado. E, na verdade, ele é o responsável pela existência de uma área aqui no Brasil. Ele, ao longo da vida, ele mudou de áreas com pelo menos 5 vezes em áreas completamente distintas. E ele dizia que era isso que dava dor de cabeça a ele. Mudança de área. Quando tinha pensado dentro da mesma área, não tinha problema. Ele começou em álgebra C-estrela, ou seja, completamente abstrato. Foi para a lei de conservação, onde ele tem um resultado que teve maior impacto em duração, que é talvez um dos raros exemplos de existência global de solução de problemas de Cauchy. Depois, por um longo período em teoria quântica dos campos, ele mostrou como é que se faz matemática aplicada, colaborando com algum outro cientista de alto calibre. Depois disso, ele passou para a dinâmica dos fluidos computacional ou não computacional em vários aspectos e aplicações. Por exemplo, interfaces entre fluidos, instabilidades, escoamentos em meios porosos, elastoplasticidade. E, recentemente, antes disso, fluidodinâmica estatística, que ele ajudou a fundar áreas que agora são muito populares, como quantificação de incerteza e problemas de escalas múltiplas, que hoje em dia são nome de jornais. Ele teve da ordem de 250 publicações nessas áreas e também em política científica, onde ele sempre advogou que a ciência deve ser feita em conjunto. Além disso, ele teve cerca de 50 alunos de doutorado, eu fui um, de modo que com isso a influência aumentou. Ele recebeu uma quantidade de prêmios, que eu não sei listar. Eu não sei se eu disse também que ele esteve, ao longo da vida, em meia dúzia de instituições. É um pouco irrequieto. E é sempre uma pessoa que eu gosto de ouvir suas opiniões, frequentemente não apenas em relação a assuntos científicos. Então, please.
Thank you, Dan. I want to start by acknowledging an outstanding group of people that I've been privileged to work with, and over a longer period of time, many others, including, as it turns out, I learned scientific computing from Oliver McBrien and Dan Marchison, and that was many years ago. Now, as the title suggests, I really want to try and find a link between fundamental issues for mathematics and fundamental issues for physics and engineering. And it's not so common that you can establish those links, so I'll let you be the judge of how well this actually plays out in this context. So turbulence is, for sure, one of the most enduring challenges of classical physics, certainly of fluid dynamics, and it is also probably the most controversial. There's a saying that the only thing two people agree on in turbulence is that everybody else is wrong. So why is there so much controversy and so little resolution? And I don't want to put it in print, but one could say so little progress. Of course, that's a question that has multiple answers. But I've identified two which have a clear relation to mathematical issues. And the first one, the first one is non-uniqueness of the solutions. And that is a catastrophe as long as you don't realize that it's true, because you try to do things, you get inconsistent answers. If you realize it's true, you can compensate, and so it's easily solved, but only when you realize there's a problem. And I also want to deal with convergence questions for large eddy simulation, and with a new conceptual framework. And I must say it's not totally new, because it's the framework I'm going to propose has been used in conservation laws for probably 20 years. And what's new is to take this, what you might say is a little bit of a recherche piece of pure applied mathematics, and use it in a central way in a numerical computational scheme. And that is very new. So large eddy simulations, simulations of turbulence have to do with how much turbulence you resolve and how little you resolve. And large eddy simulations are the most accurate simulations you can do at the present time, and probably for the foreseeable future for large-scale engineering problems. It is hopeless to resolve all relevant length scales, which might require factors of 10 or 100 in improved resolution, and that means 10 to the fourth power, 100 to the fourth power of computer resources. It simply isn't going to happen. So the idea of large eddy simulation is you resolve some of the turbulence and not all of it, and that's the best you can do. And so these are state-of-the-art turbulence calculations. A more engineering model is to not resolve anything and model it all. Now, the idea is that if you resolve the problem-dependent details or at the large scales, the engineering details are typically the large-scale features, and the universal parts of the problem, which don't change from one problem to another, are the small scales, and those you model. And that's what large eddy simulation is. So in this sense, I want to discuss convergence, and there's missing scales. What do we do about that, and why is it such a big problem? Let's see. Well, the real reason is that traditional notions of convergence do not apply. I think the traditional notion of convergence is you have two solutions and you look at the difference, and the difference you apply some norm, such as L1, you integrate absolute value, something like that. You take your favorite norm on the difference of two solutions, and it doesn't work. And that's because when you resolve the problem, you always have more little eddies. You have turbulence with a lot of eddies, fluids going around like this. And you resolve it at the level of the grid, you put in many more grid, and you have little eddies that you couldn't see before. So whatever you do, you see new phenomena when you refine the grid, and it's, in some practical sense, convergence seems to fail. Now, we'll eventually prove a theorem and say that isn't true. We'll prove a theorem with some hypothesis. All theorems have hypotheses. I don't have to apologize too much for hypothesis. We'll eventually prove a theorem and says that it does actually converge, but it's just so slow and so painful that with finite budgets, as we all have, and finite computer resources, as we all have, you just don't get there. And so in a practical sense, it doesn't look like it converges. So in fact, whoops. In a practical sense, convergence doesn't mean the mesh is set to 0, because usually you can refine at most 3 levels, 3 levels of mesh refinement. So convergence means whatever you can see on 3 levels of mesh refinement. And so we're really talking about the asymptotic behavior as the mesh is varied over 3 levels of refinement. So let's think about an observable. So you have a solution, and I don't like these L1 norms because they are troublesome, and they're sort of non-convergent. So we fix a functional of the solution. So you're building an airplane wing. You want to know what the drag is on the airplane wing, and the drag is an observable of the solution. And every problem comes with one or several important observables. Now, sometimes these solutions are at an engineering detail at the level of the engineering phenomena, and they're large, and sometimes they're small. So if you want to do chemical reactions happen because molecule A and molecule B touch each other. And so you have to get atomic level resolution to see the forces that drive the chemical reaction. So that is permanently below the grid level. And so we call those micro-observables. And for micro-observables, we need a new method of convergence, which I call stochastic convergence. So we're going to bring in random variables in a way which is not normally used in numerical analysis. So typically, stochastic convergence refers to the mean and the variance. And you can get a lot of mileage out of that. The people doing the stock market discovered that the variance, which they call the volatility, is an important observable, and it has an economic value, and you pay good money to buy volatility. So it's an observable phenomenon, and it actually exists. But it's not the whole story. And if you want to do a chemical reaction, which has a nonlinear term with an exponential, Arrhenius kinetics or whatever, and power laws out in front, you have some nonlinear function of the, and you can't get that without full convergence of the probability distribution or its integral, the cumulative distribution function. So we want to get full convergence so that we can get convergence of chemical reactions. Now, for people that do computing, that's called finite rate chemistry. And that's more or less the other side of the moon, and so as practical world is concerned. People don't believe they can do that. So I have a recipe where we can, in principle, get to finite rate chemistry. So the probability distribution, which is a solution considered statistically, the probability distribution is spatially time-dependent. So we have space-time dependent solution statistics. So we have a space-time dependent measure to describe the solution. Now, fortunately, that concept was invented years ago and used very successfully in conservation laws and a few other areas. And it's called a Young measure. So actually what we're claiming is that the solution in a turbulent problem is really a Young measure. And if you have stochastic convergence of the PDFs or the CDFs, nonlinear functions of the solution converge. And this is a very fundamental point because that says that chemical reaction, the chemical reaction rate, Arrhenius kinetics, is a convergent function of the solution. Normally when you take limits and you have weak limits and compactness, which is usually what you get, and a convergent subsequence, that's fine for a linear process, but a nonlinear process simply doesn't tell you anything at all. So this is a much stronger, although it looks weaker, convergence is actually much stronger. So a Young measure is a space-time dependent measure, and you can differentiate it in its sense of weak integration by parts, and you can substitute it in the PDE, and it can be a solution. So these are possible solutions, and they've been used by conservation law theorists for decades. They extend the notion of a weak solution. A weak solution says you take your solution, distribution solution, multiply it by a test function, integrate by parts formally, and if you get the right identities, then it's a solution. That's a weak solution. Now, this has the same idea, but instead of integrating over space and time, we integrate over space and time and solution variables. So some people explain Lebesgue measure as opposed to Riemann measure by slicing up the z-axis instead of the x-axis, and it's that kind of an enterprise. So the z-axis, which is the solution variables, the density, the momentum, the pressure, whatever, are not fundamental variables. They are variables that can be integrated over. They have statistical values. You can integrate over them as well as integrating over space and time. And then you have to put in a test function that's a test function of all those variables, the solution state variables, the momentum and the density and so on, and space and time also. And you integrate that extended test function, and that's the formal definition of a Young measure. So we consider numerical convergence in an LES sense of Young measures and the associated CDFs. Actually, we get something a little bit stronger than that, because that's weak. It depends on the test function, one test function than another. We get norm convergence of the CDFs in terms of L1 norms. And that's numerical. And this allows convergence of atomic level observables in a statistical sense. So we don't say whether atom A and atom B touch each other, but we say what is the probability that they're touching each other. And then what is the chance that they're going to react? Well, you don't say that either, but you say what's the probability they interact. But if you have a large domain, then you can say how much you're actually reacting in this domain, because those statistics will be satisfied. So it's really adequate, really, for doing combustion problems. Now, I want to digress a little bit and bring in Kolmogorov statistics. So V prime here is a fluctuating, this is a fluctuating turbulent kinetic energy. So you take the Fourier transform and you integrate out the angular variable, so it's a function of the absolute value of the Fourier variable k only, and then it behaves like k to the minus 5/3. And there's an epsilon. I should have put the epsilon in front because that's quite important. It behaved like epsilon k to the minus 5/3. That is probably the most significant result in turbulence. And it's a little disappointing to read the proof, because the proof you can do with high school algebra in a page and a half. So don't let anyone tell you it's shallow. It's not shallow, but it certainly isn't complicated. So that is the fundamental statistics. And the point of large eddy simulations is that you get into the turbulent, into the asymptotic region. So people typically draw figures that look like this. So this is K, and this is the energy E. And it typically looks something like this. And then at some point you get some viscosity or something, and it sort of falls off like that. And this slope here is minus 5/3. And the height of it is the epsilon. So you could just as well have a slope that looks like this, and they would be different epsilons. Okay, so that's classical Kolmogorov statistics. Now, a very nice theorem, which I proved with Guichang Chen, is to take this as an assumption. That's the assumption of the theorem. And those of you who are skilled in mathematics, I think, will recognize that this is a Sobolev inequality. It's a Sobolev inequality because you can multiply v prime by a power of k, a positive power of k, and it's still integrable. So it's still in L1. So v prime with a positive power of k is still in L2. So that says it has a fractional derivative. And in fact, the fraction is something less than 1/3. So it has a little bit less than 1/3 of a derivative. And that is a mathematical version of Kolmogorov, but not usually thought of that way. Now, it turns out that the existence theory for Euler equations and Navier-Stokes equations is very delicately balanced. And it's basically impossible, but it's just impossible by the smallest little amount. And you do anything and you push it over. Now, a new Sobolev inequality is a little more than a small amount, and it does push it over. And you get a theorem, and the theorem says that the solutions converge in an LP space. So, in fact, this is the pointwise convergence. I first of all told you you can't do it, and then I prove a theorem and say you can do it. So what am I really telling you? I'm telling you mathematically, if you had a computer that was 10,000 times what it is today and a moderate-sized engineering problem, you could get it to converge in this manner. In a practical sense, this theorem is not going to help you. But conceptually it says we don't need the Young measures. We don't need the stochastic convergence. You can eventually do it the old-fashioned way. But eventually is another century. And for this century, I think for the professional lifetimes of everyone in this audience, this theorem sits in the background, but you can't use it in a practical sense. So you're stuck with stochastic convergence. But at least you know that ultimately there's a real limit out there. Now, there's actually a theorem by, I'm blocking on the name, I think Shashkavili, and a collaborator, and they prove convergence in the sense of Young measures without this hypothesis, but they also don't get the nonlinear terms to converge, so you don't actually know that it's a solution. This says that the nonlinear terms converge and the limit is a solution. So it's a strong theorem, but it has stronger hypothesis. So you get new vortices as the mesh refined, but the new vortices get weaker, and therefore you get convergence. Okay, but anyway, we still need stochastic ideas. So that's the summary of this slide. So how do we go about realizing our stochastic convergence? Well, the brain-dead way is you perturb the problem in some random way, and instead of doing one simulation, you do 10,000 of them. And since you can only afford one, that's a dream also. We can't do that. So what do we do? And it reminds me very much of the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that you can know a particle's position if you forget about its velocity, and you can know the velocity if you forget about the position, or you can have a trade-off. And the trade-off is given by the Planck constant h. And you can get so much information from the velocity and so much from the momentum. So what we do is we apply that idea to the numerical analysis, and we coarse-grain the spatial resolution. That throws away information. So in other words, we put in big mesh blocks where we compute with little mesh blocks. So let me draw a picture of that. So this is the coarse grain. So we collect all the information in a whole bunch of local mesh blocks, and you get some spatial resolution left, and that's the spatial resolution that indexes your Young measure from one spatial point to another. And you throw away a lot, in terms of spatial resolution, and you might think that's bad, but it's actually good because when you throw it away, you can catch it on the way out and do something else with it. And just like Heisenberg said, if you throw out some position information, you use that lost information to get velocities. And exactly what we do here, because the velocity is a state space variable. So on the coarse grid cell, you collect all the solution values without regard to their relative position inside this block. They all have the same position. Take all those and take it a finite approximation, numerical approximation to a CDF. So you have a finite approximation to a measure on a coarse grid block. And that's how you turn one simulation into a Young measure. And of course, there's a lot of judgment as to how coarse you make this and so on. And we did some experiments and we have some recommendations. But that's sort of a technical point. The main point is you lose spatial information. You pick up state space stochastic information. And the nice thing about this idea is that it absolutely fits turbulence like a glove. It fits turbulence like a glove because the spatial statistics tend to be somewhat uniform and change slowly, whereas the detailed fluctuations within a statistical family changes very rapidly. So you use the coarse graining to say, well, the statistics are gradually changing as we move around in the problem space. And then you use the CDF to get the statistics within a coarse grid block. And then we get convergence in a norm sense, L1, which is a little better than the theory that I've been talking about. And the convergence rates are painfully slow. Painfully slow. And why is that? Well, we're still investigating. We don't have a theorem. We can probably answer that question. But let me throw out two ideas. One is that anything involving statistics is likely to have a square root of n in the convergence rate. That's the law of large numbers. And the other is that we're looking at a function which is not C infinity. It's 1/3 differentiable. So you use your favorite fourth order numerical method, and what happens? Delta x to the 1/3 power. Well, it depends on what you look at, but it could be worse or better. But you're going to get a fractional order of delta x for your convergence. It doesn't matter if you have a 16th order method, because that isn't in the solution, the 16th order. The 1/3 power is in the solution. Well, that is one set of problems, and now I want to come to another set of problems. This is completely disjoint part of the talk. Eventually, we probably unify them. I wonder if I skipped something. No, I did not. Okay, so I got into numerical non-uniqueness. Non-uniqueness, and that's a crisis only because it isn't recognized. It's non-uniqueness where people expect it to be unique. And so what happens? They go out and do something, and someone else goes out and does something, and the two things should equal each other, and they don't. And they should equal experiment, and neither of them equal experiment. So it's a crisis. So you not only get solutions that depend on the taste of the programmer, but it's very seldom the taste of the programmer overlaps with the measurements of an experimentalist. So what did we do? Well, we evaluated published solutions. I think that's fair game, isn't it? We didn't cheat by doing that. And we did a direct comparison in our own code. We modified the code to pretend we were changing the numerical algorithm, and we got different answers. And then we have a theoretical explanation, and finally we have a cure. So I think this is somewhat of a complete theory. And there's no theorem here, but I hope the mathematicians appreciate that there are fundamental mathematical ideas floating around in all of this discussion. So the non-uniqueness is not widely recognized and therefore not compensated for, and that's what makes it such a problem. Computer codes with identical physics models, each one apparently converging for the identical problem, but they converge to distinct solutions. And I think this is such a bad problem that people have swept it under the rug and claim it doesn't exist because they stopped talking about it. Code-to-code comparisons are useless And the common response is like killing the messenger. Common response is to kill the messenger. But the experiment is the only tool that can actually resolve the problem, so killing the messenger is really bad news. So we review earlier examples, and it turns out there's a history of non-uniqueness in science. And in every case, the resolution was a turning point. So flame speed, I'm going way back. That's probably before many of your people's time. But if you read Courant Friedrich's Chapter 1, you discover that there's a big issue about the flame speed, and you better put in the, I guess it's the Damkohler number or the Prandtl number. I think it's the Prandtl number. You have to put in the Prandtl number, which says you have to specify the heat conductivity. Otherwise, you get any flame speed you feel like. And then there was a big issue, again, I think before everyone's time, about shock polars. And as far as I know, this extended to wind tunnels. And they built 2 wind tunnels to measure the same shock polar angles. And they got different answers. And they were very upset. And finally decided that there was some missing physics. So in all cases, the problem of non-uniqueness is that the problem is not fully specified. And the cure is to specify the problem. And so for turbulence, the non-uniqueness is treat turbulent transport correctly. Okay, so here's a beginning of a theoretical argument. I think you'll appreciate this. This is theoretical physics, but it's so simple, I don't think it'll be over anyone's head. The dimensionless parameters, that's the first thing a physicist does. Look at the equation, count the number of parameters. Now, compressible turbulent mixing has n plus 2. There's a Reynolds number, and there's a ratio of diffusion coefficients. N is the number of species. Diffusion coefficient bulk to shear. There's two viscous coefficients, and the ratio is a dimensionless number. And then there's n minus 1 species coefficient number. These are Schmidt numbers, and there's a Prandtl number. So there's n plus 2. And the idea is you set one of those to infinity, it disappears, and you're left with n minus 1. How can you possibly have a unique solution with n minus 1 dimensionless parameters sitting there? What in the world are they supposed to do? Well, okay, so that's a physicist's theoretical proof. I think it probably was within the scope of everyone's understanding. And you can turn that into a more formal proof because the idea is that there's a limiting process. You get to infinity by a sequence of finite numbers, and you get there, you have to specify not only the Reynolds number, but the Schmidt number and the Prandtl number. And so as you go off to infinity, there's multiple paths to infinity. And each path, in principle, could be a separate limit. And that's where these n plus 1 parameters come in. They parameterize the limiting process. So my conjecture, this isn't a proof, but my conjecture is that each of those paths, if they give you a different limiting set of dimensionless parameters, probably give you a non-unique solution for some problem. But if you take an extreme case and you go off to one edge of parameter space, you can force some of the coefficients to not go to 0 in the limiting process. So you end up with different equations. So how could you possibly have the same solution with different equations? So there's a theoretical argument. Cure for non-uniqueness is to add a description of something that interacts with these missing degrees of freedom. Now, I'll explain where they come from, but these are called subgrid scale terms. They have to do with the parts of the simulation that you have not resolved, and it influences what you do resolve. So if you're doing weather forecasting and you model clouds, but you don't have room for raindrops, you'll still get wet when you go out in the rain. So the unresolved physics can have some consequence on the resolved scales. And these subgrid terms are supposed to do that. I think we have a formula up here. This is the simplest of them, the Reynolds stress. So it's the difference between the average of a product and the product of an average. And I think you all know that's bad news. And the fact is that when you look at something on a grid, you're taking basically a mesh block average of a continuum variable. So these averages up here, they're simply part of the finite difference methodology. You can't get away from that. And the Reynolds stress is as simple as these, and there's a whole series of these. I just don't want to complicate what is a simple story when explained in this manner. So the idea, and it goes back to Smagorinsky, is you put in a model and you approximate it by a diffusion term. So this is called turbulent diffusion when you model it. And everything's fine except the coefficient. There's a missing coefficient. And that's one of the reasons turbulence is so controversial, is that it has undefined parameters. And you go from one experiment to another, they keep changing and so on, and it's sort of ugly. Now, there's a theory that's come out of Stanford called a dynamic model. You can compute the coefficient theoretically, and then you get all the missing parameters. So this has actually now become a parameter-free method of calculating turbulence. It's a little more complicated, but that's roughly what it does. And how do you estimate that parameter? Is that you put in some aspect of Kolmogorov theory, and if you compute up to here, and out here you model, you know which of these curves you're on, and so you can extrapolate downwards, and you can see what you should have been doing in on the unresolved scales. So that's more or less the idea. It's plausible. It's plausible this whole method should work if you're in the asymptotic region. And that's the fundamental idea. Now, I'm skipping over some complications, but that's deliberate because I want to present the part that's easily understood. However, we're not out of trouble because the numerical truncation error, your delta x, your sleepy old delta x, you typically know, those of you who do numerical work know that there's always some kind of numerical diffusion. And you're trying to model turbulent diffusion, so these things are like first cousins, and they get mixed up with each other. So in fact, the numerical method also serves as a subgrid term. And sometimes people like that, and they say that's why we don't have to bother with the real ones, because we'll put in just the numerical stuff. So in fact, you have a problem here, which you had to do the validation, you have to take this into account. Now, normally for Eulerian schemes, typically the numerical transport is larger than the subgrid transport. And so the fact is that Smagorinsky, which allows you to add stuff, doesn't allow you to subtract anything. There's no such thing as a model that has negative viscosity or negative diffusion. That's mathematically unstable. It's bad news, and you can't do it. So in a sense, you could say that if you have an algorithmic problem, you're really stuck. Now, we get around it with front tracking, and so our full package is like this. But other people who don't want to do front tracking have a way out, and it is so unbelievably ugly that no one has thought about doing it. But I'll tell you what it is. If you want to try it, you can be the first and publish a paper on it. And the idea is that the momentum equation is much easier to solve well than the concentration equation. So you have this huge numerical effect in the concentration equation, a minimal one in the numerical equation. Now, the ratio is that Schmidt number. So you have a ratio of good quality to bad quality, and that says you can only model a certain range of physics that has the same kind of stuff. Most physics is actually the opposite. So how do you cure this? We cure it by fixing the concentration equation, and that's the front tracking. That gets rid of this numerical diffusion. But if you don't want to do that, how can you recover when you don't know how to fix the bad stuff? What you do is you degrade the good stuff. and it's so ugly that nobody's ever thought of that. Everyone is so proud of getting the best possible momentum equation that money can buy and cleverness can buy. And what you want to do is make it 4 times worse. 4 times worse, and that'll compensate for the problem in the concentration equation, and then you get a Schmidt number that agrees with experiment. Okay, now you do it. Anyone that wants to can write a paper on that.
And that's viewed as a regularization.
What's that?
Can you interpret this as a regularization of your original scheme in a certain sense?
I don't know how you want to interpret it. I don't know. You can write a paper. If you feel like it, I'll be a joint author with you. Okay, so anyway, that's really, you're not completely cured, but there is a route out. It's rather ugly, and this route I think is elegant. I like it, but anyway, whatever. So our algorithm has the front tracking, which I'm not going to talk about in detail, but the idea is to control excess diffusion in the concentration or the thermal equation, which is where it typically is large. We have large eddy simulation. We have dynamic subgrid models. So that's the basic algorithm. And we've applied this to Rayleigh-Taylor mixing and Rickmeyer-Meshkov mixing. Rayleigh-Taylor mixing is heavy fluid on top of light fluid, and it's like water on top of air, and the water comes down, but it comes down and drops in unstable flow patterns, and is a model of that unstable flow pattern. Rickmeyer-Meshkov is something similar, but there's a shock wave that goes through the two fluids. And this is related to inertial confinement fusion application, which is a problem we're involved with at the moment. So here's a little review of Rayleigh-Taylor mixing. The fluid advances just like Newton tells you to. This A is a normalized, this AG is normalized gravity with buoyancy correction. And if alpha was 1/2, you'd say, hey, I learned that in high school or college. But alpha isn't 1/2, and that has a drag in it, so there's some drag, and that's the only experimental number. G is gravity. Okay, so we did a lot of simulations. We got the right answer, and we were a little bit lonely because everyone else gets a different answer. They thought we must be wrong because we were agreeing with experiment. And they all agreed with each other, so the experiment was wrong. If we agreed with the experiment, we must be wrong also. So we were a little bit lonely, and we had to get out of that bag. And so we did uncertainty quantification. What the claim was that the experiments had garbage initial conditions, which excited different modes, and so the experiments weren't clean, and you couldn't bother modeling them, and so on. So we looked at the experimental data and did uncertainty quantification for the initial conditions. And we did the uncertainty on the mixing rate, and we got, well, et cetera. Let me go forward. So here is not the initial conditions. This is the third experimental plate. And this is the first one that has enough of a developed interface you can actually see the instability. So if you look at this thing carefully and sort of with a microscope and go half blind, you can figure out the Fourier mode numbers of the different perturbations along here. And we did that, and we put that, this is plate 3, and we ran it backwards in time using the equations to plate 1, which was the initial conditions. And then we ran plate 1 modified forwards in time to deal with the experimental results, and we were right on the money. So here is the initial conditions, and this is by wave number. This is there's a power law, and it's just like everybody said. Everybody said, well, there's a power law, and this power law will get you there. Now, the power law will get you there, but you have to be up here. If the power law is up here, it would affect the solution. Power law turns out down here, it doesn't. And here's the time evolution. You see, you lose the power law right away. The nonlinear dynamics takes over the power law of the initial conditions. The initial conditions, while they have the power law, they don't have the coefficient, and they have no effect. So here's our solution with the experiments and 3 solutions. We did the predicted perturbation from our analysis we did that time minus itself, in other words, times 0, and we did that times 2, which are very generous error bars. And that gave us plus or minus 5% on the growth rate. And the one that was done just right was right on the experiment. So we got basically perfect results with the uncertainty quantification. I think the community has pretty much accepted this now as being scientifically correct. So here's an example, and you'll see in a little bit the solution running right through all those data points. So this is the Rayleigh-Taylor instability. This is the front tracking solution. You can see we have a fairly complicated interface that we're computing, and here we're going right through all the data points. How about that? The standard for this subject is a factor of 2 relative to experiment. So we plainly did not fall into that category. So we did a lot of validation tests, and here they are. And in most cases, we have no discrepancy whatsoever. With one case we can probably fix, but we haven't gotten around to that. Now, compared to other people, the standard for this growth rate is about 100% effect. In other words, there's a factor of 2 relative to experiment. But if you don't like the experiment, look at these people relative to each other, and they don't agree. There's a 50% variation from one programmer to another. So it's a complete disaster if you're talking about doing science. Now, the alpha does change depending on the experiment, and we can tell, since we have a 0 to 5% effect, we can see this 20%, and it's due to experiment A and experiment B have different physical parameters, and we can see that difference, and so on. So I think we have a pretty good influence. Now, I think the numerical issues I've already discussed, so I don't have to go over this. Now, I want to talk about validation, and the validation of the experiments are at Reynolds number 35,000, and we'd like to go up close to infinity in Reynolds number. Now, there aren't good experiments at the very high Reynolds number. So what do? We're stuck. And we've already said, well, you can't do anything without experiments. Now, it turns out that from 35,000 to infinity is actually a small perturbation, because it's really 1 over 35,000 compared to 1 over infinity. So it's a small perturbation, and you can do that with a little bit of courage. You just do that mathematically. It's not that we like it, but there's no better way to do it. So that, because it isn't experimental, it's mathematical, we call it a verification. Verification means the mathematical correctness of what you're doing. Validation means the experimental correctness. So we go to infinity with a verification study. The effects are not 0, but they're all small. So it's a mathematical and perturbative extrapolation from a validation. And so this is a common practice when the extrapolation is small. And so all we're saying is this is a small extrapolation. And here we do this on a different problem, which is a Rickmeyer-Meshkov, circular Rickmeyer-Meshkov. This sort of looks like an ICF problem, inertial confinement fusion problem. So here's the initial conditions of the shock wave on the outside, and it goes in. Here it's already gone in, and it's gone in through the interface, which got unstable, and then it went back out a second time, and it went highly unstable. This is the outgoing shock wave. And this is the basic solution, and this is a refinement, a blow-up, and this is another blow-up of this. So you can see it's unstable practically on all length scales, highly unstable. And this is some kind of visual proof of convergence. These are concentration versus temperature, so they're 2 scalar variables. And these are 2 different grid levels, and you can hardly see the plots here, but if you look at the projections on the axes, the marginal distributions, you can see they're practically identical. So we put them into our machinery for measuring L1 norms of CDFs. And the mesh error was about 6%. I didn't display that. This is different. This is a change in Reynolds number. This is about 8%. So the change in Reynolds number is only marginally observable relative to the mesh error, but it's there. So we believe it's a real effect, but small, and so an 8% effect, and that is the extent to which we can do the verification infinite Reynolds number. And this is some more studies of the same problem. As you go to infinity, the Reynolds number as a fraction of its value at infinity, it starts converging. And this is the turbulent versus the other transport coefficients. There's something strange about the heat conduction. And what's strange about the heat conduction is that we're modeling inertial confinement fusion plasma physics problem in which the heat conduction comes from the electrons. The electrons are light. They have a huge heat conductivity, and then they couple to the ions, and the ions pick up this large heat conduction. So basically, everything but the heat conduction is governed by turbulence. Okay, so now we decided to change the turbulent transport. So we changed the Schmidt number to 1/10 of nominal and 10 times nominal, and we compared the results. And you can see the marginal distributions at this end, they're quite different. If you had a numerical algorithm that did that, we did it sort of by hand, but you could bury it in a numerical algorithm if you wanted to. And that's what you'd get. Now, I think I'm running out of time, so I will skip over some of this. This is the use of the W star, the convergence of the CDFs and L1 norm. Let me just do this plot here. So this is the coarse grid, the medium grid, and the fine grid. And I think it's evident that there's convergence as you go through there, but we want to make that quantitative. So these are the CDFs in all of those supercell blocks. This is the medium, and this is the fine, and you can see convergence as you go across. And this is the L1 norm of the difference, coarse defined and medium defined. And the point is there's a lot more blue, a lot more deep blue. Blue is good and red is bad, yellow is bad. No yellow over here and more blue. So it's plainly converging. Not as fast as we would like, but it is converging. Okay, so conclusions. We have essentially perfect validation for the macro observable. That's the growth rate. And the accuracy within the error bars. We can distinguish between different experiments, etc. We decided that the experimental regime is relevant to the high Reynolds number limit. We have convergence of the CDFs. I didn't go into detail on that. This is, in fact, still under study, so we have, I would say, not as clean results as we have up here, but we have some results. And we have a program for uncertainty quantification and verification validation, uncertainty quantification for atomic mixing. So the V&V proposal is you validate where you have data and you extrapolate where you don't have data, etc. The benefit of stochastic convergence. The nonlinear functions converge, so you do finite rate chemistry. We have a project with Stanford on modeling a scramjet, and we're still struggling to see whether we actually get this accomplished or not. But in principle, it should be correct. And it seems to reflect the true nature of turbulent flow. And this is the theorem I mentioned with Guichang Chen. If we have K41 velocity statistics, then you get proof by compactness and convergent subsequences. We get an LP convergence solution. So in the end, you don't need the L1, the stochastic convergence, except that you do need it. Then there's a study of the renormalization group as a model for turbulence. That's sort of a classy study. We didn't get tremendously good, useful results out of it, but we got a good measure of intellectual understanding, and where there's an RNG fixed point that's associated with LES, etc. So, thank you.